Okay, so 2 questions up here. What is gravity, and which object experiences a greater force, the sun or the earth? All right, we'll explain that second picture here in a second. The first one, what is gravity? Okay.
What is gravity? 9.8 meters per second squared.
Okay, so Katrina says 9.8 meters per second squared. Rex says a force.
I disagree with 9.8 meters per second squared.
If Rex says the force and Katrina says 9.8 meters per second squared, are they both right?
No.
No, because 9.8 meters per second squared is an
Acceleration.
acceleration. Good. So we're dispelling one great confusion. When I say what is gravity, I'm not looking for the acceleration due to gravity. Okay, remember we've taken those 3 accelerations due to gravity. So we've taken those 3 words off the front, right? And we've just been used to saying gravity is negative 9.8 meters per second squared. That is the acceleration due to gravity because gravity is a force.
I said that.
I know you did.
I got it.
Scott, what's up?
Taylor.
I got it.
I heard it.
It's the attraction between one object and the other.
Okay. So Skylar says it's an attraction between gravity is an attraction between one object and another.
Force.
The force. So force of attraction.
Yes.
Okay. What does attraction mean?
It's like
Valentine's Day.
It's like when all the ladies.
I will tell you how this whole gravity thing can prove there's some attraction between you and your Valentine. Even if they don't want to be your Valentine, it's still attraction. We'll get to that later though. All right.
You
So-
told us that it physical science.
Rex, what'd you say? I know. I gotta use the same jokes over and over again.
Yes.
What'd you say? You forgot? Yeah, Kyle, what were you saying?
Is that like when something moves closer to something else?
That's what attraction means. They move closer to each other. All right. So, any other ideas for gravity? So Skylar says the force of attraction. Anybody else? Okay. Now, the Earth is right here. The sun is right here. This picture is not to scale. If this picture was to scale the sun, we then need to be really, really, really huge. Like taking this whole wall huge. Okay?
So could it be the size of that circle right there?
No, it'd be bigger than that. It'd be bigger than that. Or the Earth would be much, much smaller. Okay? Think about your whole little grain of sand in your hand, right? And your head would be like the sun, and the grain of sand would be the Earth. That's how much bigger they are. Okay? So it's very huge. The sun is very huge. The Earth is very small. All right? Now, which object experiences a greater force of gravity? The sun or the Earth? Okay? It's kind of one we can vote for. Who thinks the Earth experiences a greater force? Oh, that up or down? Okay.
Put it up,
1, 2, 3, 4, 5, 6. Kind of. Okay.
Wait.
Who thinks the Earth experiences a greater force?
That's what you just said.
That's what you just said.
Oh, who thinks the sun experiences a greater force?
Who doesn't know?
It's the
Okay.
same.
Who doesn't know? Okay.
Who's gonna learn?
Okay, so we have 6 for the Earth, 0 for the sun, 4 who didn't know. Who didn't vote because they didn't like my options? Don, why didn't you vote?
I think it's the same.
You think it's the same. Which one orbits, though?
The Earth.
The Earth is moving, right?
No, the sun orbits around us.
Well, if you're geocentric, then it's okay. All right. But the Earth orbits around the sun. So because the Earth moves around the sun, a lot of people think that the sun doesn't experience a force of gravity, but the Earth does. Okay. Or they look at the idea, the sun is a lot bigger than the Earth. The Earth is moving, so the Earth must feel a bigger force. Right? Those of you that chose the Earth as experiencing greater force, does that kind of fall in line with what you're thinking? Because its mass is so much, because the sun's mass is so much bigger, the Earth experiences a bigger force.
The first one that you said, where it's Earth orbiting, that's why I think.
Okay. So Monty, you think it's that case because the Earth is the one moving, right? And the Earth is following an orbit that's kind of circular, right? So that means it experiences a centripetal force towards the sun, right? Is the sun experiencing a centripetal force towards the Earth?
No.
No.
It's not going in a circle, is it?
Well, I don't think
No.
maybe one.
If it wants to, it can. Okay.
I think it's experiencing a force behind a trip.
That's centripetal force.
Yeah.
Okay. Now, what causes that force?
Math.
What causes the force? Gravity. Jesus, gravity, mass. Okay. All right. So let's say it's us then. We guys, we experience gravity on the Earth, right?
Yeah.
Right. Why do I experience gravity on the Earth?
Because the Earth is big and small.
Okay. So the Earth is big and we are small. That's why I experience gravity.
Right. Like if you were on Earth.
Because you have way less mass.
Because I have way less mass.
You're getting pulled to the Earth.
I'm getting pulled to the Earth. So, which way, guys? Which way does the force of gravity pull me?
Down.
Down toward the center. Down towards the center kind of sounds centripetal-like.
Yeah.
So, isn't the Earth rotating?
Yeah.
So, isn't it the rotation what's keeping me pulled down?
No.
Right.
Yeah.
Okay, guys, I understand this is kind of informal, but I still want you to pay attention and not talk about other things. Okay? So, if the force I feel is down towards the center, that's kind of centripetal-like, isn't it?
Yeah.
So, is it the Earth's rotation that's causing gravity?
No.
Or is it something else?
Something else.
Who thinks the Earth's rotation causes gravity? Who thinks something else causes gravity? Sandra, what's that something else? What? You don't know? Jose, what's that something else? You don't know. Imani? It's your girl inertia? Locke?
The density of mass on Earth.
Which one? Which one? Mass here. Okay. Those that are saying gravity is attributed to mass, that is correct. Okay? Gravity, or the force of gravity, is a result of an object having mass.
So babies have less
Babies have experienced a smaller force of gravity because they have a smaller mass. But that does not mean that their acceleration is different. And I'll prove to you later on that regardless of mass, everything on the Earth experiences the same acceleration, as long as they're the same. Alright, so, guys, so, those who are saying that gravity is attributed to the mass of the object, that is true. Every object that has mass experiences gravity. Every object that has mass also exerts gravity. Okay? So right now, I'm exerting gravity in all of you. Okay? So, what that means, since I'm exerting gravity on all of you, I'm also exerting gravity on this marker, right? So, if I drop this marker, will it fall towards me?
No.
Where does it fall?
Towards the center.
Towards the center of what?
The earth.
The Earth. So the marker falls towards the center of the Earth because the Earth is a very, very large mass. Am I a very large mass? Oh, you're too mean. Okay. Comparatively speaking to the Earth, I am not a very large mass. Now, maybe compared to other people, maybe I am. Now, if I was out in outer space, far away from the Earth, if I were to drop this marker, where would it go?
Float up, maybe.
It would just stay.
It would float here, but it would feel an acceleration towards
You.
me. The same way that when I drop this marker, it feels an acceleration towards the Earth. Now, the acceleration would be much, much smaller
How would it float?
because my mass is much, much smaller than the Earth.
How big is it? Why would it
How big is the
float
Earth? We'll do that in some examples here in a little bit.
Do we really watch that movie?
No.
I've never seen it.
No, I've never seen it either. That's why we're not going to
It's
watch
not. It's
Why
not a
don't
good
you watch it?
It's
it. Guys, we're going to learn about what this whole idea of gravity and where it comes from before we even watch any movies. Yes?
Why does the marker float towards you?
Why would it float towards me? Because I have mass. And we'll get into here in a second when we start talking about the Law of Universal Gravitation.
Well, then in the movie Gravity, the girl floats away from a spaceship, but she really should float towards it.
No,
Oh.
the Earth is a lot bigger, a lot more mass than the spaceship.
If she's floating away.
So she gets pulled to the Earth. Okay?
So she's getting pulled towards the Earth.
Now, if the spaceship wasn't there, then she'd actually be pulled to her acceleration towards the Earth would be greater.
And then flying.
But since the spaceship's there, the spaceship also has mass, so it's pulling on her towards the ship. But the Earth is that much bigger, so it wins as a bigger
No,
force.
she's floating with both.
So she,
She shouldn't float away from both.
She's floating just like out in open space.
All right,
Because someday it was like some force pushed.
something exploded.
Yeah, and it pushed her.
Okay. All right. So what is gravity? Now, to really figure out what gravity is, we need to go back in time a little bit and start kind of where this whole study of the astronomy, the whole study of these planets started. All right. So I'm actually going to go back a slide. So back here, Kepler's laws of motion. The reason I'm starting here, all right, is if I did not talk to you about Kepler and Galileo and Ptolemy and Tycho Brahe, I think I'd be doing those men a tremendous disservice because those men committed their lives to coming up with these three laws, okay? Without those three laws, okay? Guys, please focus. Without these three laws by Kepler, Newton would never have been able to come up with his universal law of gravitation. All right. Now, Kepler came up with these laws by looking at some data from this guy by the name of Tycho Brahe. Tycho Brahe was a very, very, very adept studier of the planets. He kept really good data on where planets were located in the sky. He did not want to share this data with Kepler, so Kepler had to wait until Brahe died. Okay? But before Brahe collected all this data, there was this guy by the name of Galileo. Does anybody know who Galileo is? Okay? He was an astronomer, among other things. Okay? Now, Galileo was alive around the time where the Catholic Church was not just the church, but was also the head of the state. All right? The Pope was in charge of everything. Okay? Now, the Catholic Church had a belief in what's called a geocentric universe. Anybody know what a geocentric universe is?
When the Earth is in the middle.
The Earth is in the middle. Galileo had a belief in a heliocentric universe. What's that mean? The sun is in the middle. Now, Galileo was not the first astronomer to think this. There's a guy by the name of Ptolemy, way back in ancient Egypt, who thought the same thing. But his ideas did not agree with the Greek philosophers of the time. Everybody jumped on board with the Greek philosophers that the Earth was the center because we're most important, kind of arrogance, and everything rotates around us. But it's really just a perspective thing because we are too rotating as we orbit. But we can get into that later if we take an astronomy class. So, going back from there, Ptolemy had the idea of a heliocentric universe. Galileo conducted a lot of observations that followed that heliocentric idea. He did not release his idea about a heliocentric universe until he was close to dying, because once he released them, what happened to him? He was put in jail. And he stayed the rest of his life in jail because of his beliefs about a heliocentric universe. That heliocentric idea eventually was adopted by science, and Tycho Brahe could conduct all of his experiments and observations with that in mind. So then all of his observations were then accurate. And Kepler then, once Brahe died, got all of Brahe's information and was able to develop these three laws. Right? Now these three laws, the reason I'm bringing up is they are what's going to help Newton come up with his law of universal gravitation. Right? So, the first of Kepler's laws is that all planets have elliptical orbits. So now some of you guys are thinking, what's an ellipse? Well, an ellipse is kind of that piece in the little kids' puzzles that looks like an oval. All right? You guys call oval, it means ellipse. Right? Does that make sense? Yeah. Okay. Now, what this law says is that the sun is at one of the focuses. An ellipse is made by having two dots and stretching a string between the two dots, and then drawing a figure using those two strings. Those two dots are the focuses. The sun is at one of them. Okay, so there's our sun. I know the sun's not green, but we'll go with it. The other focus is nothing. There's nothing there. Okay? All right, 2. If you draw a line connecting the sun and the planet, the line will sweep through equal areas at equal time intervals. Okay? So what that means is if here's Earth one day and it's here the next day, if I draw a line connecting the sun and the Earth like that, I have this little triangular looking sector, right? Okay? Now later on, if the sun is here, let's say this is day 1, day 2, day 15 is the sun, the Earth, or the planet's here, right? Where will the Earth be, or where will the planet be on day 16? Will it go the same distance on the ellipse, or will it go more distance on the ellipse? It'll cover more distance. So this is 1 and 2. Let's say this is 15 and this is 16. All right. The reason why it does that is this area and this area must be equal. That's what Kepler's second law says. Basically, it's saying is that as things get closer to the sun, they move faster. All right, because their radius is less, their acceleration is more. We'll get into that when we get to Newton's law. All right, and then the last one is for two bodies orbiting the same object. The square of the ratio of the periods is equal to the cube of the ratios of their radiuses. Now you're probably thinking ellipses, radiuses. Well, most of our planet's orbits are almost circles. They're very close to being circles, kind of like the circles I try to draw. They're very close to being circles. All right? But they're still ellipses because the radius isn't exactly the same to all points. All right? But they are almost circles. So they almost have a radius. They have a mean radius. Right? Now, what this is saying, if this is the sun, and this is one object, we'll call it the Earth. Okay? Not to scale again. And this is another object. We'll call this one Jupiter. Okay? What this law is saying, Kepler's third law, is saying, if I take the period of Earth and divide it by the period of Jupiter, okay, how long it takes to go complete revolution, and I square that, it is equal to the radius of Earth's orbit divided by the radius of Jupiter's orbit cubed. Okay? Basically, it's saying that objects that have bigger radiuses take longer to go through them. Okay? So if they take longer and they have bigger radiuses, that means their velocities could be less, could be the same. But then it basically says that the further we get away from the sun, the longer the orbit takes. All right, does that make sense? Okay. So Kepler's 3 laws, and the reason why I'm starting there is because those 3 laws are what drove Newton to ask this question, what is gravity? Okay? Now, Newton and Kepler, they came up with laws. All right, what is a law? Something that can't be broken, okay. Well, there's 2 things in science. There's laws and theories. All right? What's the difference, Katrina? Law and theory.
All laws been tested and it's actually, I don't know.
Okay. A law has been tested and proven, right? So a theory can become a law. So you guys have this idea that a theory, when it grows up, right, becomes a law. They can't. Okay? Rex is right, they cannot. But some students believe that they can, or someone may have told you in the past that they can. Right? Now the difference between a theory and a law. A theory is an explanation. Okay? It's someone's attempt to explain. So theory is an explanation. Okay. A law is observed. Okay? It isn't the same thing. A theory is an explanation for why something happens. A law is an observation. So Kepler's 3 laws, those are all based on observation. He's not explaining why they're ellipses. He's just saying that the planets go in elliptical paths. He's not saying why they sweep out equal areas. He's just saying they do. Okay? Same thing with Newton. Newton's law of universal gravitation does not explain why we have gravity. It just explains what's happening. Or just observes what's happening. Right? And his law, Michael, follows his observations. There's this guy who came after Newton, his name was Einstein, much after Newton. He came up with a theory of gravitation. Einstein's theory of gravitation does not refute Newton's law of gravitation. Because Einstein's trying to explain. Newton is just observing. Okay, does that make sense? Okay, so that's the difference between a theory and a law. All right, are there any questions? Alec, you have a question? No? Okay, just wondering. All right, so now we've all built up Newton's law of universal gravitation. Now, why is it called Newton's law of universal gravitation? Because it applies to all the planets in our universe? Because this is just for orbiting bodies? No. The reason why it's called Newton's law of universal gravitation is because it applies to every mass. In the universe. Do you have mass? All of you have mass, right? This law applies to you. Some of you have more mass than others, right? Some of your mass is more dense than others. Okay? But we all have mass, right? Right? So this law of universal gravitation applies to every single one of you. Not just planets, Skylar. Okay? It applies to anything that has mass. It applies to rocks, applies to carpet, applies to tables, applies to chairs, applies to paper. Okay? Anything that has mass, this applies to. Right? Not just planets and suns. Not just planets and stars. Right? Now, Newton's law of universal gravitation. What Newton came up with. Now, he studied mostly the planets. Right? So the first time he stated his law, he used the planets. All right? So Newton said the force. Actually, I'm the gravitational force between the sun, I'm going to call this big M, because the sun's got a big mass, and the Earth, little m, that's got a little mass, is proportional to the product of their masses. What does product mean? Multiply, good. And inversely proportional to the distance between the two squared. Okay. What does inversely mean? Divide. Okay. So Newton came up with this relationship. Remember this sign alpha? You guys called it the fish last time. That means proportional to. Okay. So what he's saying is that the force of gravity is proportional to the big mass times the little mass divided by the radius squared. Okay. Now this agrees with Kepler's ideas. Yes. Okay. Now this agrees with Kepler's ideas because Kepler said that as planets get closer to the sun, they move faster. As the radius gets smaller, what happens to the force? It increases. Good. As the radius gets smaller, the force increases. If the force increases, what happens to acceleration, George? Force goes up. What happens to acceleration? You don't know. Rex, what happens? It gets bigger. If acceleration gets bigger, what happens to velocity?
Increases.
It increases. Right? It agrees with what Kepler told us. Right? So that's what Newton figured out. Now, do you think Newton was okay with this proportionality? No. What did he want that to be? He wanted this sign to become a what kind of sign? Equal. An equal sign. He wasn't able to do that. Okay. But one of his countrymen, a guy by the name of Henry Cavendish, was able to find a constant. Okay. What's one constant in mathematics? You know, some symbol that always means the same thing. Pi, good. Pi always means 3.141592 and keep going, right? It always means that, doesn't it? Yes. And there was a Greek, I think it's Aristotle. Okay. Aristotle was looking at a whole bunch of circles and he found that there was always a constant ratio between the diameter, the distance through the middle, and the circumference, the distance around the outside. And that proportion was pi. Okay. Now, this Englishman by the name of Henry Cavendish, and he actually did this in 1798, about 100 years after Newton. Okay. Henry Cavendish set up an experiment where he had a very large mass on two ends of a connecting rod. Okay. Then, in the middle of that rod, there was a pivot that he set a smaller rod on that had two smaller masses attached to it. Okay. Now, universal gravitation says that these masses are going to what each other? Pull each other together. Okay? So, in order to figure out how those get pulled together when they're released, Cavendish put a mirror on here, and he focused a beam of light on that mirror. Now, as this rod rotates, what's going to happen to the outgoing beam of light? It'll change where it shines. It changes directions a little bit, right? That deflection, that change in direction, using that change in direction, Cavendish was able to figure out a constant that turned this proportionality into an equals. Okay? Based on whatever masses he put in here, the ratio of the masses did not, saying that backwards. The ratio of the masses, regardless of what they were, they always ended up equaling out that same number, kind of like pi in the circles do. Right? That same number is called G. And this is what's called the universal gravitation constant. Okay. Now, why are there meters squared? So it cancels the radius squared. Why are there kilograms squared? Cancels the masses. So then we end in N. What's N? Newtons, which are force. So Cavendish was able to take Newton's equation and turn it into the one we use today. And this right here is the law of universal gravitation. Does that make sense?
You know, my brain is fried.
Your brain is fried now? Well, that's the most difficult part. Because all this says is that the gravitational force between two masses, right, is equal to G, some number, times the product of the masses divided by how far they are apart. Okay? Now, this force of gravity is what type of force again? And I can't believe I did not write it down here. What is it? It is a force of... It's a force of attraction. What does attraction mean?
Jesus.
Pulls things together. So that question we had earlier with the sun and the earth. Once again, not to scale closer. Okay? What's the force of attraction? Which one experiences a bigger force?
The Earth.
The earth. Why?
Because the sun's bigger.
Because the sun's bigger. Is that right?
He's not even in this class.
I know we have a guest student today.
Mean
Right?
girls.
Be smart.
Is that right? No, it's not right. How many equations do you see down here? One. Right? The gravitational force is the product of the two masses divided by the radius squared. There isn't a big mass equation and a little mass equation. There is one equation. So what that means is if the force from the earth on the sun is some number, we'll call it 10 newtons. I know it's not the case. Then the force of the sun, the force of the sun on the earth, if it's 10 newtons, then that means the force of the earth on the sun is also 10 newtons.
Equal.
Yep.
Going on.
And this agrees with which one of Newton's laws?
First.
Third. These forces
77.
are a third law pair. Okay? Remember what third law says? I push on something, it pushes back equally on me, right?
Yeah.
The sun pulls on the earth pulls on the sun
This
equally.
science is so easy.
Yeah. So, does that make sense, guys? Does that make sense?
Yeah.
Okay. Remember we talked about this earlier. The earth pulls down on me, right?
Yeah, sure.
I pull up on the earth.
Yeah.
Then why do I accelerate when I jump off the table? Because I weigh less, because I have a smaller mass. So why does the earth orbit the sun and not the other way around? Because the earth has a smaller mass. So the earth has a smaller mass, so its acceleration is more noticeable. Right? Does that make sense?
Yes, now we're done.
Are there any questions?
Nope. But
We have
thanks
10 minutes left. We can't be done yet.
Yeah.
There's plenty of time.
Thanks for frying our brains.
No problem.
Don't pull it down.
Okay. So let's try an example, because you're going to want to have a example underneath your belts for your homework.
We have homework tonight?
Yes, you have homework. Not tonight, but it's homework.
Don't we do it tomorrow?
Not due tomorrow.
Okay.
Okay. So on this example 10, universal gravitation, there are four parts. We'll go through each one individually. Now, all this information that I'm using is found on page 173 of your textbook. Right? So A says, what is the force of gravity exerted on the Earth by the sun? The mean distance between them, the average distance, is 1.5 times 10 to the 11th. All right. So what is this right here? 5.9736 times 10 to the 24th. That's a mass. I forgot to put kilograms. Okay. What's this? A mass. This one is the mass of the sun, much bigger than the mass of the Earth, right? Like 10 to the 6 times bigger. Wow, it's big. Okay. So 5.9736 times 10 to the 24th. That's the mass of the Earth, right? Okay. That's my little m. Big M is
1.9891
good in unison. Nice. Okay. What's the radius? Yep.
Of what?
1.5 times 10.
Good. 1.50 times 10 to the 11th meters. Right? So, that's the information that I have, right? Okay. So, one more thing I need is big G. 6.67 times 10 to the negative 11th. Newtons, meters squared per kilogram squared. Right? Now, to find the force applied to the Earth
Let me try that on.
What equation?
What's that?
All right, now.
Alright, whenever you're ready. Wow.
We need to plug into this equation. Okay? Can you guys give that a shot?
No.
Yes, you can.
We can't.
Plug in.
I'm waiting for someone.
Okay? Sample 10A.
Okay, I'll do that.
It's not? No, it is. Oh, okay. Good. I'll talk to you. I got I can't. I gotta have to practice to exhibit.
Okay.
So I was thinking, I mean, if you want, I could just bring Alvin so you just.
That's fine.
I'll be,
Good.
alright, good deal.
Alright? Alright, sounds good then.
Don't tell us.
Did ECR go well? Yeah.
Just a lot of live and
Oh my
Yeah.
it's pretty good.
You're going back on Thursday then?
Yeah, Thursday or Friday.
Okay.
I mean, unless Canol talks to Granville, I can get Epi, but
Okay.
we'll see.
Hold up.
Hold up.
You guys just told me you couldn't do it. Now you can.
I'm trying to do it.
Awesome. Good. Keep trying.
One more time.
Love it when you guys try.
I hate when I try.
You hate when you try?
Raise your
Oh, effort is the key to success. What?
I'd rather fail, so.
Okay, should you use ease or times 10?
Ease.
Ease, especially on your radiuses.
Oh, Branch. Do we have a Branch? You know what? I'm gonna do this.
Now I'll get George back his calculator.
We hate
Wait, what
this
is the
work.
MN
Right.
squared?
George ain't doing nothing.
Don't worry about
I
it.
didn't even finish it.
Cal, get George back his
I'm
calculator.
almost done, Branch. Branch, come on.
There's your calculator.
George, you use that
Come on, guys.
Give me math squared.
4 more minutes.
Let's just all drop out.
Okay, so
I got it.
Kyle has
Wait, don't say the answer.
I'm not going to say the answer.
Look at
Okay.
this.
So we plug in G.
How do I use it? How do I use it?
Yeah.
I got it, but I think I'm pretty sure it's wrong.
We plug in mass. 1 second. Is it really big?
Yeah.
We plug in both masses.
Yeah.
Oh, that's wrong. We'll get that in a second, Rex.
The comma bar.
Okay. 5.9736 times 10 to the 24th.
If you have an E, you don't have to put the time sign right.
Right. And we plug in the radius.
I got it.
So that's everything plugged in.
Man, I forgot.
Okay?
Oh, you gotta put the square.
Do we have
You
to?
need parentheses?
Yeah, you have to.
You don't need parentheses, you can just put multiplication. So you can just do this.
No.
Multiply,
They're at the bottom.
multiply.
I'm at the bottom.
Now if you use the E, you don't need parentheses. Okay? So in your calculator, if you enter it like this, 6.67 E negative 11 times 1.989 E 30
Okay, Branch.
That's what I did.
times 5.9736 E 24, and then divide that by 1.5 E 11 squared,
Yeah, girl.
and that'll work.
I forgot.
Oh!
Hey, girl.
I forgot a
That's what I
one.
got.
All right.
We're gonna have to do this on the
I forgot a one,
So-
Branch.
What?
We're gonna have to put this numbers on the daily basis.
Yes.
Wait, don't forget the one, Branch.
Oh, and then 99 one. Sorry.
Party.
Okay, guys, hold on a sec. So what do we get? 6.67 E negative 11.
I got
3.5,
3.5 E22.
Say.
Isn't Yoda 24?
Yeah.
Yeah.
What?
The prefix.
Oh.
Wow, I thought we were never going to use
Go back to
that.
sleep.
Okay. So guys, this equals 3.52 times 10 to the 22nd Newton.
Why didn't you go back?
Yeah. So that's the force of gravity. Guys, hold on a sec. It's like 30 seconds left. This is the force of gravity exerted on the Earth by the Sun, right?
Yeah.
What's the force of gravity exerted on the Sun by the Earth?
We don't know.
Equal. It's
Same
that.
thing.
Right there,
Yeah.
guys.
Same exact thing.
Same
Wow,
thing.
I slept through it.
I know.